Hi, welcome to another episode of EV Fundamentals. Today, as requested under the last episode, I will talk about CAN. So, let's look at some material that VW, Volkswagen, have come up with to teach their employees CAN. So what we see is control unit A, B and C, all connected to a common bus. That seems to act both as receive and transmit bus. So basically what CAN is a serial bus on the physical level, much like RS485, because it has differential signaling for better noise immunity. But it has much more than that. It also has arbitration. Because the principle of CAN is that every control unit just dumps values out onto the CAN bus that it thinks can be important to other control units. And then the other control units just use whatever information they need from the CAN bus. So it's like a database that's being updated in real time. You can just listen to it and receive values from it. The speed of the front left wheel, or is the handbrake pulled? All that is just constantly transmitted onto the CAN bus. And to be able to do that, what we need is arbitration. So with the amount of messages on the CAN bus, it's like a probability of pretty much 1 that eventually 2 nodes will transmit at the same time. And of course that usually is not possible, but on CAN it is. When 2 nodes transmit at the same time, the dominant message will win. So for every bit a node transmits, it will read back the CAN bus, and if there's a difference and it finds out it is the recessive node, it will stop transmitting its message and the remaining part will just be transmitted without any information loss. It's pretty clever. So basically, when a node loses its arbitration scheme, it just transmits its information later on. And it will find a time slot where there is no other traffic. Now, what is also defined by CAN is the format of the actual message. So as opposed to RS232, which just defines a byte as the fundamental transfer unit, CAN actually defines a frame, just like Ethernet, for example. The frame is pretty simple though. It contains a message identifier and the actual message content, and then some checked information that's not really relevant for the application. Or actually what it is relevant for is that you can be sure that whatever you transmit or whatever you receive from the CAN bus is valid data. There's no flip bits or anything, because the CAN hardware does the CRC checking, and when there's an error, the message will be retransmitted. The identifier basically tells us what we find in the message content. And I've made this highly sophisticated picture here. So basically the identifier here is our color. So let's say orange is identifier 1, pink is identifier 2, and then green is identifier 3. We have defined, upside down, sorry about that. Let's take this one off. So we have defined that the green message contains inverter, speed, and what else? Voltage. bus voltage. We have also defined that the pink message contains currents, and the orange message contains digital pin states from the inverter. So whenever we see a green message, we know what it contains, how we have to interpret it. What we don't want, and that's why I took this off, is another pink message that contains a different content, because then we really have no way to know how to interpret the frame if there's two messages on the same CAN identifier. So that mustn't happen. So within the CAN network, you have to distribute the CAN IDs in a meaningful way, so that there's no two IDs with different content. Yes, so let's look at the implementation a bit. It's a bit boring, to be honest. I mean, as opposed to the resolver implementation, it's not too much exciting stuff happening. So first we initialize the CAN hardware. We set the I/O pins, we set the baud rate, and the only interesting part could be the filters, because, like I said, every node dumps its information into the CAN bus, and then every node will receive that message. And I have listened to the CAN bus on the Volkswagen Touran, which isn't even a top-end car, and it has a message rate of 1500 messages per second that are floating around on the bus. Now you want to make sure that your controller only actively processes messages that are relevant for it, because otherwise you would be getting 1500 interrupts per second, and I don't know, you will discard most of them, and just 5% of the messages are relevant for your software. So for that reason, I think it's even specified within CAN that the CAN hardware has to identify a hardware filter mechanism to basically filter out messages that are not relevant for the given controller. So we configure filters here. It's again pretty boring, just writing two registers, and then finally we enable the receive interrupt. So whenever a relevant message comes in, we are notified and can process it. What else? Let's have a look at the way messages are sent. Not in detail really, because it's also quite boring. So what we've got is a CAN send map and a CAN receive map. So basically the send map contains, we can map all of these beautiful values onto the CAN bus. So we can specify we want the operation mode on CAN ID orange, ranging from bits 5 to 7, for example. And that's what the CAN send map contains. And likewise the receive map maps incoming CAN data onto these channels, onto these entries here. So each map is an array of this structure right here, an ID map. So basically we specify CAN ID orange contains the following items, and then the items are in CAN pos, and that like maps one-to-one to what you see on the web interface. So you can map, for example, UDC with a gain of 10 to get like 100 millivolt resolution, starting at bit 0 and stretching over 16 bits. And then basically let's make a sophisticated drawing. Yeah. So if this is the full length of our CAN message is 8 bytes, 64 bits. The first 16 bits contain the UDC, the bus voltage, times 10. That can happen, for example. So yeah. So then in the next item we can specify how we want to put speed. I think that's what I wrote onto the green card here, how we want to put speed into the CAN message. Yeah, so then the code, there's like a cyclic function. It can be called every 10 or 100 milliseconds, and it goes over all CAN messages we define and puts together their content by iterating over the position map. And then, yeah, you can see some scaling and masking and shifting going on. I mean, yeah, just look at the code. I hope it's fairly obvious. And then finally we send the message that we've just generated. And that has maybe an interesting detail. So the CAN transmit function goes into a hardware abstraction layer and puts the CAN message into the various registers to have it sent. Now, of course, the hardware isn't unlimited. It has 3 TX, I think it's called mailboxes. So if we send more than 3 messages, all the mailboxes will be full, because the code runs much faster than the messages are actually pushed onto the bus. So yeah, if we have more than 3 messages, this transmit function will return a false result, and we start filling up a software send buffer. And if it turns out we do that, we also enable an interrupt request, TME, transmit map message empty, something like that. So we get an interrupt request once the FIFO has some free space to take a message. And in this interrupt routine, right here, all we do is we use the transmit function to transmit a message, one message, from the send buffer. And then we decrease the number of pending messages. And once we get into this function and we find that there's no more messages to send, we just disable the interrupt request. That's it. Likewise, in the receive interrupt, there's also quite a bit of hardware stuff going on. So as opposed to the transmission FIFO, there's actually 2 reception FIFOs for whatever reason, maybe prioritization. Yeah, each FIFO also contains up to 3 entries. And yeah, we do some iterations. So we look at the first FIFO and we keep receiving until it's empty, and then we look at the second FIFO and keep receiving until it's empty. And now when we receive a valid CAN message, we look up the ID in our CAN receive map, because the ID tells us how to interpret the content of the message. And then we do some more boring iteration and take out all the data from the CAN message and map it to our data module. And if it's a parameter, we use the set function, which results in a range check and the callback function being called for the parameter. And if it's a value, we just set it. So for example, the CAN-based throttle just directly sets the values of pod and or pod 2 to control the throttle. No range check is done by the data module because it's done by the software logic. And we also update a timestamp because we want to find out when we get a timeout. So when you haven't received a valid message for some given time, we assume a timeout, and for example we set the throttle value to 0. Okay, and I'm getting emails, that's great. Yeah, so that goes on in reception. There's also a special CAN ID, and I have to admit this is a bit hackish. So this part here is CAN open. So what CAN open does is it puts another layer on top of the basic frame format here. So it gives a meaning to the various identifier bits, and it also gives a meaning to the various message bits. And we can have a look at that. So basically, if the first, what is this? Some bits in the beginning of the CAN identifier work out to 6, we are looking at a CAN receive SDO, service data object, and the remaining, I think, 7 bits encode the node ID. So that's also CAN open specific. We can assign an ID from 1 or 0 to 127 for identifying the nodes, and I've just hard-coded, given the inverter, CAN open identifier 1. Just until someone complains, I will make it configurable. So yeah, the service data object is quite useful because it sort of standardizes something we want to do. So let's take a look at how a service data object kind of assigns a meaning to the 8 bytes. So the first byte is a command byte. You will see what that means later on. Second byte is an index byte. Third byte is a sub-index byte. And the remaining 4 bytes contain the data associated with the request, the payload. So let's look how we process a service data object. So first we map the generic CAN data into the SDO data. Now, if the SDO index is 2000 hex and the sub-index is a valid parameter index, so basically parameter index means boost has index 0 and fweak has index 1 and so on and so on. We go into this subroutine here, and now we look at the command byte. And the command byte can be SDO write, that's like a standardized command, 40 hex. And in that case, we call the set function. And the set function does the various range checks, and if it's valid, we set the command code to write reply, which is 23 hex. If the set function returns false, 0, yeah, whatever. If it returns an error, we know it's a range error, so we reply with a command code of STO abort, which I think is 80 hex. Yeah, and we specify the error as a range error. Our given value was out of range. And now likewise, if our command is read 22 hex, we simply get the parameter and write its value into the payload. And then we send a reply, and you can see we always send a reply. So for example, if the index is not meaningful to us, we send another STO abort, 80 hex, and the invalid index error code. And as you can see, the STO reply is happening on a different ID. It starts with 58 hex and then the node ID. And yeah, that's all there is to that's all that's relevant from this service data object to us. You can also have expedited, what's it called, like messages that stretch over more than one message, and then in that case you would do multiple sends. Yeah, but it's not relevant for us. We'd only do simple 32-bit transfers over STO. And this code, I won't go into that. Basically, you can map. You can edit the ID map, the send map and the receive map by sending an STO as well. Yeah, so last thing I want to talk about is how we save the CAN map to Flash. Because when you set up all your CAN maps, you don't want to lose it on the next reboot. So the interesting part is in this function here. So internally, the CAN send and receive map encode the parameter position just with the index, because it's the fastest possible way to do it. So like said, boost has index 0 and so on and so on. Now if we were to save the map to the Flash in that way, that's fine. It would work, and I've actually in the past I've done it like that. But now what happens if I add another parameter? Call it, whatever. Now all the parameters below it will be assigned a new index, obviously. It's all incremented. So that's not good. Then our CAN map becomes invalid. For that reason, in addition, every parameter has a unique ID, and I do some bookkeeping up here in the comment. Whenever I add a new parameter, I give it a new unused ID. So that's what we do here. Before we save the CAN maps to the Flash, we replace all the indexes by these unique IDs, save it to Flash, add some CSC, and then reverse the operation basically. And likewise, when we load from Flash, we check for valid CRC, and then we also, because we've saved it with the unique IDs, so before we can use it, we have to replace the unique IDs by the index. Yeah, so I think that was the most relevant parts of a practical CAN implementation. I hope that you found something useful for your own project in this episode. And if you do, also give it a thumbs up. And otherwise, discuss down below what you would still like to know. Thank you very much for watching. See you next time, and bye bye.